Welcome everyone. We will be talking about fixed satellite services and radio astronomers in V-band. I'm Charlotte Ramiro. I'm a junior and I'm studying electrical computer engineering.
I'm Lilo. I'm senior and I'm studying computing.
Okay, so an introduction to our presentation. We'll be talking about the incumbent of radio astronomy operating in the V-band, so 40 to 75 gigahertz, and the entrant of fixed satellite services or FSS broadband satellites in the 37.5 to 42.5 gigahertz allocation. And our coexistence issues are adjacent and in-band interference, wherein NGSO FSS constellations pose threat to radio astronomy. And you can see here the band allocations for radio astronomers and FSS, and especially focusing on the left here in 42.5 to 43.5 gigahertz, the adjacent interference between the RAS allocation and the FSS downlink. So what is radio astronomy? This is our incumbent group, and essentially what they do is listen in on specific radio frequencies to study celestial bodies at frequencies outside the visual range. So you might know this photo of the black hole from a couple years ago, which became quite famous. And they mainly listen in on continuum emission and spectral lines. And other important facts to know about radio astronomers or radio astronomy is that they require really large antennas that are really, really sensitive, so they can pick up really faint and far away signals. There are also hence built-in remote and really deserted areas, which are also radio quiet zones, which means that satellites that are in their path are really dangerous to radio astronomy because these telescopes can't be easily moved or easily escape interference that is coming over them.
Moving on to our entrant, fixed satellite service and GSO constellations. So what is fixed satellite service, FSS? It's a radio communication service between Earth stations using satellites. So why companies would want to build NGSO constellations in V-band is that compared to K-band, V-band allows more bandwidth and throughput. However, it is more susceptible to rain fade, and although this is a challenge, it's a technical challenge that can be overcome. In the history of wireless communications, it's been a slow migration towards higher frequencies, so this is a really natural progression for NGSO constellations to move up to the V-band. More about NGSO constellations. So already over 4,000 satellites have been launched, operating in the K-band, that none in the V-band so far. However, in November of last year, there were applications for over 38,000, or around 38,000 satellites in the V-band. This is sure to raise radio astronomers' concerns. Some of the V-band players are listed here. Main ones you might know are SpaceX and Lilo. So a timeline of the issue, going back to 1932, Carl Jansky is the founder of radio astronomy. He is the one that discovered radio emissions coming from the sky. Ever since then, radio astronomers have been building telescopes, but then jumping forward to May 2019 after the first Starlink launch. This launch raised concerns mainly for optical astronomy due to the brightness of Starlink's satellites. However, it also raised radio astronomers' concerns at that time as well. That was following that launch was Satellite Constellation Conference 1, where they worked on where radio astronomers and stakeholders all came together to work on solutions for this radio frequency interference and optical interference. Following that, the next year they continued to have Satellite Constellation Conference. Moving forward to this year, the Center for the Protection of the Dark and Quiet Sky began operating, and they have done some great work already. Laying out the geometry of the interference. The interfering signal caused by the SpaceX V-band and GSO satellite system is a downlink on 37.5 to 42.5 gigahertz. As you can see, the satellite will be transmitting down to its Earth station, but whenever it's coming in the direction of a radio astronomy Earth station, or even through sidelobe interference, it can cause interference to be received by the radio astronomy Earth station. And and that is represented by that equation on the bottom left.
So in terms of solutions, we came up with a lot of things. Some of them are more temporary, and some of them are more long-term. So in terms of temporary solutions or mitigations, one of the things that we found was SatHub, which has software tools that help astronomers avoid satellite passes and correct affected observations. And while this is helpful for now, it becomes less effective as more satellites are launched because they're a lot harder to avoid and the observations are more affected. Other design decisions that help mitigate interference are building array telescopes as opposed to single beam, which are slightly less affected by interference, but they're still effective. Likewise, adding radio filters to satellites to protect RAS telescopes, such as OneWeb has implemented, is helpful in reducing interference, but still does not completely eliminate it.
Moving on to proposed solutions, the NRAO and SpaceX have been continuing to collaborate on experiments to quantify the interference. They have been trying things such as steering satellite beam transmitter beams away from telescope sites, and they've been finding some success using phase delay as well. So their continued work will hopefully lead to some solutions. As well as the Center for the Protection of the Dark and Quiet Sky, they have already had some successes in optical astronomy with the SpaceX VisorSat and DarkSat, and their continued efforts to bring together stakeholders to work on solutions and to have a good relationship, I think is important because this issue can only be solved through collaboration and coordination. Another solution is to find ways to inform FSS about radio astronomy operations and have the FSS adjust their operations to avoid a certain downlink channel so that radio astronomers can use that channel for observations at that time. We heard about this work from Dr. Christy Cree, and we think that is potentially the best solution moving forwards. Lastly, there are radio frequency interference recommendations from the International Telecommunication Union, and we will talk a little bit more about that next.
So one of the ITU recommendations are our equivalent power flux density, which is basically the power of the FSS satellites that are received by the radio telescopes. And as you can see in this regulation, although it does say how much interference can go into radio astronomy stations, it's a lot more general and is not very specific to FSS constellations. So this would be a regulation that would need to be specified further.
There's also interference to noise. That is another metric of radio frequency interference. First step to mitigating interference is to understand it, which is why the Olin Satellite Spectrum Technology and Policy Group is working on a tool to quantify dynamic interference to noise.
And so finally, our conclusion is a mix of different solutions. So one would be to inform satellites about RAS operations and adjust those operations to avoid those downlink channels. We also would like to require operators to steer satellite beams away from telescope sites and consider continuing the use of RF filters on their satellite systems. And finally, to work further on RFI limits and mathematical modeling of EVFD and IOPRA.